So, yeah, let's get started. I am working on my PE cough dumper. You know, if we go over here, I wrote a little bit about it here. The binary and object file deep dive project. And for the last couple weeks, what I was doing is dumping out PE cough files, which is one type of binary and object file format that's used on Windows. And the dumper has gone to the point where it's pretty good. So the next big step that I think would be worthwhile is to go make a generator instead, right? So instead of reading in a PE file and dumping it, we're going to do start with an empty program and generate out a PE file and see if we can get a PE file that'll actually run. Now this could take a few rounds because I don't exactly know what the bare minimum is that it's going to take to make this work, right? So we could start with just figuring out manually how to construct a file, like piece it together and try to figure out what that minimal starting point is going to look like. Or we could start with the generator program and use the generator program as our way to spit these things out. And I think I prefer the second option because even if we get some of the stuff would be easier, like getting the headers just right, might be a little easier at the beginning with just manually typing in the file. At some point, sooner or later, I do want the code, and I want the code to be able to do all that stuff anyways. And the code might also help with spitting out the correct file structure in a way that doing it by hand might be, or doing it by hand in the same way might be tedious. It's possible. My gut instinct tells me to do it through the code to make it easier. So go into our binary folder here. We'll do pe.gen.c, give it a header file to go with it, and dump.c generator. Gen.h base c pec grab an entry point, maybe like this. All right, and there we go. Now I need to be able to build this new project. And we need to be able to run this project. Oop, CL isn't set up. Fair enough. There we go. So now I've got gen pe.run, run fly. Whoops, you're right. That should be saying gen. All right, so that does that. When we look at gen.c, if we just want to make sure, you want to be able to do like m4 printf hello world. And there it is. All right, so where we want to get started probably is by figuring out how to put out the correct header. So let's pull up a hex editor. And we'll drop We'll drop an exe onto it. And now I want to recreate the chunk of data that matches this header here. I don't know what all of this right here is, but right here we get that. So I think this chunk here, this first, what is this? 16 times 16. So the first 256 bytes right here might be what I want to recreate, but like exactly as is, and then have the actual PE begin right here. So I wonder if I can copy that and paste it right here. And then do something like OX space Okay, and then we're gonna go OX 1, 2, 3, 4, 5, 6, 7, 8. Mark77, hello. How are you doing? All right, so now I need to start outputting my file here. I could make a string 8 list and try to put everything that I want in line with it that way. I could also do like some kind of out. Here's the file. Here's the position. PE DOS header. Here's the data. So I set a position, a raw position, and a data block. Nice. All right. I'm not sure if that's the API I'm going to want, but somehow or another I want to build up this file and write it. So, what can we do? Let's just make this thing real for now. So we're going to have a little PEGen file. PEGen begin file begin. Young Lane, hello. How are you doing? Oops. Have you ever had to deal with writing your own C interface for CPP libraries that don't provide one? Yes, there was one occasion where I did that, or a couple of occasions where I did that, where I wrote a C wrapper around a C++ library. CPP libraries that ship with the compiler, that is. That I don't think I have done. Why would I? So the C++, what's an example of a C++ library that ships with the compiler? Are you talking about like standard vector, or the standard template library stuff, or like I don't know what else shipped with the compiler. And you can't exactly wrap templates in C code. I mean, you can, but it doesn't. It's not this. Templates are sort of direct write, for example. Okay, yeah, sure. So I have done that. So if you look at direct, where do I have this? I thought I had a DirectX DX. Let me just go look at it this way. Examples, D3D11. Okay. So here's my D3D11 example program, and it's in C++. Now, what I haven't done in this code base is I haven't actually wrapped that in a C API, but if we were to look at OpenGL, yeah, this is under render OpenGL. So here I have my OpenGL implementation of my R API. So if we look at render abstract, all of these functions here are meant to be implemented by a renderer. So if I ever wanted to do a direct 3D11, a D3D11 renderer, I would implement all of these C functions using the C++ code of D3D11 in a separate compilation unit. Direct write. Yeah, direct write isn't really with the compiler, but I know what you mean now. When you say it ships with a compiler, I'm thinking of standard libraries for the language. And, when you get Microsoft's compiler, it's true, it comes with a bunch of system SDKs as well. But those aren't... It's a little... what counts as shipping with the compiler might be slightly confusing, right? It's like... I guess... you do get them by default when you install the compiler. So it's not inaccurate to say that. It just didn't pop in my head as an example. But I'm not sure why it's shipping with the compiler matters. I also had to do the C wrapper thing for over on GameJolt.com. If you've never been there, check it out. They have like a high score system. I don't know. Here, let's look at. Oof, shush. I'm gonna mute that tab. It's loud. Where is this? Most Undead. So this game I made years back, where we integrated with their high score table system. You can see I'm over here, crush the high scores. But we integrated with the high score system here, and this was a C++ like there was a C++ library that they provided for integrating with this, and I wrapped that in C because, you know, I didn't want to program in C++. Yeah, you can wrap a C++ template in C, but you give up the actual polymorphism, like the compile time polymorphism. The you know, once you use a template and instantiate it, it becomes code, and so C functions are always code. A C function can't become code later on in compilation, right? And you can't link to templates either. Linkers only deal with actually generated code. Templates only exist during compilation time. Templates get rendered out into instances that are just regular old code by the time they hit the linker. All right. Generated.exe, return 0. Okay. I don't think we've done any good file generation code in the code base before, so we might end up with a new layer, new helper layer, or a new base layer feature. If we end up with a good way of generating binary files this way. A good layer for that would be nice. Okay. And then arena temp scratch, get scratch. We need the scratch arena here because we're going to do a buffer that's variable length. File size. We want this to be the max of the existing file size and whatever the new max size is coming in from there. Yeah, that's fine. And then we're going to do a loop over all the nodes in order. And memory copy into the buffer plus node position, node data stir, node data size. And finally, and then just blop that right out into a file like that when it's done. Okay, now if that works, what should happen is I should be able to come in here and grab generated and plop it down right here. But it doesn't recognize this. Well, this is lame. So I guess Imhack stops being helpful if it detects an error. It's going to do like, it's going to be a picky error type of thing, which is fine because it means that I can tell if this is busted, but it's lame because I can't get it to highlight this part on its own. Alright, well that's fine. Let's keep going. We want to output a COFF header, right? So the COFF header begins right here. We need a PE signature. Put down one of those. Right, okay, let's tell this to think of it as a void pointer so it won't be picky. And then it just needs to cast right here. There's our PE signature. Oh, really? Mark 77, you've got your own single header utility libraries. That's really cool. That's really cool. How have you posted those, or are they just like a private thing for yourself? I'm glad to know that you were able to take away from that like a useful idea of how to structure your own headers to get yourself started, though. That's cool. Yeah. I've been having conversations recently with people about like, is it worth it to try to converge a community onto one base layer? Like, would we be better off if we all kind of sat down and decided, hey, this base layer here has all the main features that we think a base layer should have. We might, none of us might think it's perfect, but it's pretty good, covers a lot of stuff. We could agree to work from here together. Or should we all just get used to writing our own base layers and operating independently? The advantage to the first one, obviously, is that if I write code on my base layer and you write code on your base layer, then they can't work together. So if we were on the same base layer, there are advantages about like code sharing working better and stuff. But there's a disadvantage, which is that when we each have our own base layer tuned up exactly for our needs, it allows that to be it allows it to be highly specialized to our own style, our own way of thinking, our own problem space, and so it's much more effective than having like a base layer that's 50% on the point and 50% cruft for our use case, but then, you know, also it spares us from having to work on it ourselves and allows us to collaborate. It's an interesting question. I also don't know, like, in addition to not knowing which one is better, I also don't know how to go about getting everyone on the same base layer necessarily. So I'm just throwing it out there. Curious what other people might think about that. Interesting. Young Lane says, I'm currently writing my entire code base in one file. Am I going too far? Maybe, maybe not. I don't know. I'm actually moving towards a less header count overall. So Mr. Fourth base is now fitting inside of 4 files, and I've collapsed all of my base layer and OS layers into just these 4 files. So I'm getting more hardcore about using a small number of files too, and that's partly because I want it to be easier for other people to use my own base layer. Which I think having lots of files makes a library harder to wrangle. You know, the lesson of STB is like, if you want everyone to just use your library, do it in one file. Now, a code base isn't supposed to be a library, but a base layer, maybe a base layer can be. Maybe. Okay, so we got our magic number. But I put the wrong magic number in there, didn't I? This is the MS-DOS magic, and I don't want that magic. I want the magic PE signature. Where is our PE signature? Ah, here it is. And there it is. Now that's correct. So what happens after the PE signature is we find a COFF header. So we want to put down a COFF header here. Give me COFF header, please. There we go. Machine type. AMD 64. Section count 0, timestamp 0, symbol table foff 0, symbol count 0, optional header size 0, flags. Executable image, line numbers, local sims, aggressive WF large, address aware, reserved, 32-bit machine, debug stripped, removable run from swap, net from DLL, up system only, bytes reserved, high. Alright, let's try that. So that generates our file. Yes. Reload it. Generated. Okay, generated still doesn't... Oh, I didn't actually put the node on the file. Arena file COFF header, size of COFF header. Yes. All right, what is it saying is going wrong here? Yeah, this is still saying that there's something wrong. Oh, there we go. I had to hit it to evaluate again. Got it. Timestamp, number of symbols, size of optional header, 0. What are these two? These are the bits. Right, so we have executable image. Cool. Mark77, this hex editor is called imhex. It's a hex editor, and it also comes with like data built-in data patterns, so it's aware of a lot of formats and can sort of analyze them for you. It is very cool. I only discovered it last week when someone recommended it on the stream, and it is proving to be quite a useful tool for this project, because now I have a way to stare at my hex file, I have a way to stare at these files that we're generating today and actually see if we're getting anywhere. By the way, today what we're doing here, this is very unstructured. We don't have a specific, we have no idea how far we can get or what sort of order of things make sense to do. We're just kind of chipping away at a new thing. This is very much like a breaking ground on a new angle kind of day. So we're just throwing stuff at the wall and seeing what's gonna stick and if this direction is feasible as a next step. Okay, so we've got a COFF header here. Now I imagine if I try to run this, something bad will happen. Zap can't run on your PC. Close. Great. So I can't run that. Now let's see if we can... Let's see if we can get to the point where it will run. So I think the next thing that's missing is our COFF header does not include the optional header. So let's do COFF header dot optional header size equals, and then let's look at the size of, let's look at the size of this. And then let's put in the optional header PE32 plus. Now this needs the magic number. PE optional header 32 plus, PE 32 plus. There's our magic. Oops, this should say optional header magic, PE 32 plus. Run the generator there. Yes, reload it. And boom. So it is recognizing this as the beginning of the optional header. Although it seems a little bit off. Size of heap commit. Reserve. Yeah, how is this? PE 32 plus. Optional header size of P header 32 plus. A20EC1D. Hello. My editor is 4Coder. So let's see. So yeah, if you go look for 4Coder, you can download it for free. The default config is the one I use. And if you go to 4coder.net, whoops, we got to fix the security certificates. If you go to 4coder.net and you click on this Discord link right here, it's going to take you to the 4Coder Discord, and you can ask more questions about 4Coder there. Yeah, my config is the default one, so like you don't have to do anything. So the only thing you have to do is set up a project file. That might be what you're missing. If you set up a project file, you'll get the F1 through F12 are set up to do build. So like if I look at right now, I have F1 is build fly. And so build fly right here, footer panel equals true, right? So what you can do is just go list. If you Alt Shift X, you get the list, or if you do Alt X, you get the list of. So by default, Alt X will give you the list of all possible commands. Set do new project, and that will set up a blank project for you with like possibly one typo in it that makes it not work. But if you go onto the 4Coder Discord and ask for help setting up your project, they can get you to the point where you can do this thing. And then you just load up your project, and your project has the commands that you want to run bound to the F keys. All right, so there we go. So why is this off? So it's like, here's PE signature, architecture. Oh, this isn't using the off like it should. That will explain it. Yes. Size of optional header, 112. There's the flags, and then the optional. Size of stack commit. Size of heap, reserve, heap commit, reserved. 1. Looks like they actually have a couple of flags for the spot that I marked reserved. Number of RVAs and sizes. I think that's supposed to be the data directory count. And then a bunch of zeros after that. But why? Why doesn't it line up is what I'm asking. Optional header 32 plus, PE 32 plus. Size of optional header PE 32 plus. Stack size reserve. Yeah, these are not 8 bytes. Yeah, this is not expanding like it's a PE 32 plus, even though the magic here says PE 32 plus. Here, this one says PE 32 plus, and image base is actually an 8-byte integer. That, and that are 8-byte integers like they should be. Reserved number of RVAs. And then, boom, here become the RVAs, right? Yeah, so for some reason on this side, it's not going for the 64-bit version. There we go, it went now. Okay, so that all adds up. Cool. So now we need to fill in some of the defaults here in a way that will actually be useful. Let's see. Let's see if we have over here anything about the default values for some of these. Okay, so we have section alignment. Is 4K. So section alignment, virtual section alignment 4096. File section alignment 512. Why the difference? What does that mean? If section alignment is less than the architecture's page size, then file alignment must match section alignment. Okay, that's not happening. Okay. Okay, cool. Image base. Well, it's not any of these defaults, which is interesting. It looks like it's 140000000, right? So 1, 2, 3, 4, 5 bytes. That's 1, 2, 3. Image base. Yeah, it's definitely saying here that it's using all 8 bytes. Okay. Text voff. All right. Let's see. That's good. Major operating system version. Don't care. Major image version. Subsystem version. Minor subsystem. Win32 version value. Size of image. Right. Oops. Sorry about that. Size of image. Size of headers. 4. 1024. So this right here is like saying 1 kilobyte. So the size of all the headers. So right here, right. So this contains RVAs. Does this begin? Yeah, this is just a data section. So the section headers must still be included in that. Okay, so where this starts to get tricky is that in order to do the next step, we're kind of getting there, but we're no longer going to be able to just hack stuff in here. Sooner or later, well, I mean, one other thing we could do is we could drop in the data directories. Let's do that. Data directory count. Data directories. Give me a bunch of zeros. Yes, reload it. And so here we got 16. These should be getting parsed as data directories, but they're not. There they are. Okay. So now we have our 16 data directories, which we might want to be able to use. And so finally, we can do this. We say all of these are the headers. And out the other side from that, we want to know after we've done all the RVAs, there's finally put our raw data, the sections, right? So here's where we start getting section headers. So we're going to say up here we already need to know the number of sections we're going to have. And what happens is right after the optional headers, we get the section table. So okay, so a section table. In order to do a section table, we're going to need to look at the section header. This time we're looking at a variable length that is determined by the parameter up here. Although to put it another way, the entirety of the section concept is going to be a parameter. So for now, we're just going to hard code a section in. We're going to think a little more about how that's going to work later. So a section header. Zero 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 flags. PE section flag. Mem read, mem execute. Something like that. Let's take a look at what this one says. So .text virtual size is big, RVA small, 4096, size of raw data, pointer to raw data, pointer to relocations, pointer to line numbers, number of relocations, number of line numbers, contains code. Is read and execute. Okay, so that's everything it has there. All right, when you look at this, Right. Since the memory doesn't get copied on, we can't actually... Actually, like, none of this is safe the way I've done it. We need to go have file node just always do a deep copy, I think. Somewhere in here, we have PE, architecture, number of sections. There it is, 1. And this right here, is line 200. Yeah, they're on the same spot. So text, virtual size, RVA, size of, pointer relocations, pointer line numbers, number of relocations, number of line numbers. Flags. Why won't you pick up? Yeah, it's putting the section table in the wrong spot for sure. Here it's putting section table at 208, which is the right place for it to go. COFF header is up here. Number of sections, 7. Alright, so how are you figuring out where the section table goes? What is your logic for that? Surely you talk about a section table somewhere in here, don't lie to me. Okay. Let's just look for the word table then. Sections table, that's why I couldn't find it. Okay, so if I look at the COFF header, optional header, that's 118. We add in the size of the optional header, that's 115. 118. Oh, that's 240. Got it. Now if we look at mine, the COFF header, optional header begins at 118. The size of optional header says 112. But I asked for the size of this. Oh, but I probably needed this to be the size of this plus 16 times the size of the data directory. Yes. We run this, and there we go. Now it's recognizing the section. Okay, cool. All right, so that means I have a header, section header for the text section. If I go here and say, like, where's my section table? It now actually highlights the section table, which is good. So the next question is, where is my text section, right? And for that, I think we need to do the section header is going to want to say that the F off of this is 1 kilobyte. The V off of this dot text section virtual size RVA of 4K. So the reason for that is probably alignment. It's putting the section at a 4K boundary here, leaving space for the COFF headers to get mapped in. Now what we need to do is get just a little bit of disassembly. This shouldn't be too hard. Let's do well, hopefully you have some kind of way to turn this into... You're not going to make me go and manually turn this into hexadecimal, are you? Alright, okay. Hold on. We're going to do this a different way. Apparently this isn't... Let's just try something here. Godbolt show instruction encoding bytes. Hmm. I'm sure it's around here somewhere. Here we go. If I can just, I'm gonna have to put this on one side of the screen. Put this on the other side. Close one of the panels. $55 for the push RBP. MOV RBP RSP. MOV EAX01. Pop RBP. Ret. It's not clear why we're doing these steps here. I bet you we could do this, right? Put a 1 in EAX and then return. Let's just try that. There's our quickie program. And then we're going to we're going to set up the text section to contain that data. One, two, three, 4, 5, 6. Seven, 8, 9, 10, 11, 12, 13, 14, 15, 16. So at 1 kilobyte on the file, I'm going to put down the quickie program. Total size of text. Total size of text is going to be 16. Entry point voff. Entry point voff is going to be 4K, so right at the beginning of the text section. Oh, the image size is going to be 8K. The first 4K are for the header. The second 4K is for the text section. Cool, cool, cool. So here at 4K, we get the hex for returning a 1 and then some padding. Or it's actually, it's at 1K, not at 4K. Right. Okay. Cool. So, question: how close are we to this? Okay, application cannot be run in Win32 mode. That's fine. Let's see. Let's see about setting the Windows subsystem. See if that helps. Subsystem. PE Windows subsystem. Now my question is, what subsystem is being used here? Windows GUI, it says. What if I look at one that I know isn't a GUI? Yeah, fatsat test is not a GUI. Fatsat test. Yes. COFF header. Subsystem Windows CUI. Okay. So we want to use the Windows GUI subsystem. While we're at it, let's keep filling in this optional header here. There's some other stuff we might want to make sure to use. There's the image size and header size we set. Yeah. Subsystem we set. DLL flags. Are there any DLL flags we want? Um, okay. Looks like there are a few. High entropy VA. Dynamic base. NX compat. Terminal server aware. Okay. So it uses those flags. What else do we want? I think we want to get the stack size and heap size stuff figured out. So that's 8, 16, 20, 1 to 2 to the 20. 1 megabyte. Size of stack reserve, 1 megabyte. Why don't we look at the defaults that are listed here? Size of image, size of stack reserve. Doesn't say anything about what the default is, but I think it's 1 megabyte. So stack size reserve equals megabyte 1. Stack size commit equals 4K. Heap size reserve equals 1 megabyte. Heap size commit equals 4K. Yes, reload it, rerun the parse here. Now we're getting things like size of image. Yeah, your size of image is big, your size of image is big, my image is small. Okay. Okay, those seem to match. Those seem to match. Those match. Alright, we might have a problem with the fact that there are a bunch of empty directories, and this might not work with empty directories. So that might be the next thing we have to fill in, but let's see. Okay, maybe I need to look at operating system version numbers and stuff like that. So let's fill in those. Total size of text. Entry point V off. Did I write that down? Yeah, that one's written down. Spicy Emperor Adrian asks, "Are you making a compiler?" ? Not exactly. I am working on toolchain stuff, so I am studying. Excuse me. I am studying how to generate an executable file right now. So in a sense, Damn. Okay, there we go. At least it's out of my system now. So in a sense, I am making something close to a compiler. I'm creating something that generates a program. But unlike a compiler, I'm not doing like semantic analysis and all that. I'm just kind of mastering the file formats, and then I'm going to take stuff in a different direction. Okay, optional header, size of code, address of entry point. Okay, so here we got a big address of the entry point. I put it right there. What else do they have that I'm missing? Size of initialized. Yeah, I don't have any. Size of code. Size of code 16. Does my size of code need to be... Oops. Doesn't look like it. Have you heard about Cosmopolitan C? No, I haven't heard about it. The actual portable executable. No, I haven't heard of that. You're talking about something I haven't ever heard. I'm interested if you want to share more though. Okay, so I want to keep on trying to figure out what it will take to make this thing run. I think what I am tempted to do right now is to make a little test case. That'll look like this. Okay, and then what I want to do is I want to build fly BLD unit source path root path testing mini.c mini. I'm going to build mini, and now mini should be something I can just run without a problem. Yep, so that just runs. And now if I were to look at mini side by side with the program I'm actually spitting out, then I would actually have so mini is 94 kilobytes, whereas my generated is 2 kilobytes. So there's a lot of stuff here that is not the same as mini. Oh man. So right here we can see the entry point. Return 1. This is the same as this is what I've got, right? If I come over here and look at mine, we've got that. So that part matches. The rest of this is disassembly for other code that got generated into my program by the compiler. Now hopefully we don't actually need any of this. The hope I have is that all of this is for like standard library stuff that we can actually live without. But then the question is, we get to the end of the text section here. What else is going on? Look at all this stuff. What? So much stuff. That's so much stuff. Yeah, so we have like symbol table here and stuff. Interesting. Oh wow, this looks wild. I'm gonna have to spend time on this later, but it looks like someone's got like a polyglot style file that looks like a valid shell script and also like a valid, we have some form of valid Unix shell script as well as a valid PE executable so that it can run in lots of places. Cool. Haven't seen that before. That is a little wacky and wild and cool. Okay, so I'm trying to figure out how I'm going to sort of use the difference between this and this piece by piece. We're going to start from the beginning and just think about like wherever there's a difference to deal with it. So these are different. COFF header pointer in mini is at F240 and here it's at 01. So what's the difference there? What is this stuff? I don't actually know what any of that does. I copied this out of a different file. I don't know what that is. I assumed it would be the boilerplate that is the same on every file, but now if they're different, then maybe I need to know what they are, or I at least need to, they also both have this thing that has a rich at the end. Like something is going on. Doesn't make an interesting wide string. Yeah, doesn't make anything that I can recognize. So this is some mystery stuff. Let's just cross our fingers here, hope for the best. We're going to take the last 16 bytes out of this. Take 16 bytes out of this. Take 16 bytes out of this. Yes. Okay, so now these two should line up. And the header pointer needs to be modified. The header pointer is this right here. 0, 1. This becomes F. Yes. Okay, so that and that match, except this needs to rerun so we can get PE right there and there match. So the blocks of data don't match. We don't know what those are, so maybe there's some kind of hash or something, or they still look like a table or a set of instructions or something, but anyway. 50, 54, 64, 68, that's the architecture code. This right here is the number of sections. So this comes with 6 sections, okay? We're going to look at the 6 sections in the section table. So we've got a text section. .49664 is actually bigger than 49648, strangely enough. But that's fine. Doesn't have any of these. Contains code. Data alignment 0. Executed. Read. And mine contains code. Data alignment 0. Executed. Read. Okay. Section 1 here is an R data section. Contains initialized data, readable data. We don't actually have any data for it. Okay, data again, zeros. Read and write. Okay. P data. And P data comes with read, but not write. Okay. Next up we have underscore R data. That comes with read. And then after that, we have relock. Yep. R data with a dot and R data with an underscore. We're going to be, as we're doing this stuff, we're going to be uncovering lots of little janky, fiddly nonsense that happens. There's so much cruft in the native layer. You know, like, it does not have to be this bad, except that the legacy stuff on top of legacy stuff has just been left there, you know? And so, so it becomes difficult to wrangle. So this is readable and discardable. Blamey asks, are you exploring existing executables to try to research a new one? Yeah, kind of. So I'm studying up. Why don't we take a look at this? So here at the Mr. Fourth Lab, which you can support, by the way, to keep the projects going and to get cool benefits for being a supporter or a member, I work on various projects. I talk about them a little bit over here on my most recent blog posts, and we're working on this one right now. And the idea is to start by deconstructing the native layer tool chains that we have now to get a really good handle on them. And that way we can hopefully imagine new steps forward to make the native layer architecture more powerful, more resilient, easier to work with, more flexible, just less black boxed, you know, all that kind of stuff. Now, one thing we can't do is we can't just invent an executable file and be like, there, it's done, because the operating systems participate in the executable file so much. So we're going to have to be a little creative about what we actually are doing when we go to tear up and imagine a new native layer. We might have to figure out if the operating system is getting in the way, how we're going to sidestep that, and how a better operating system might also need to be a part of the picture. Hopefully this is research that can be of benefit to people working on their own operating systems. But even if not, we might find that the current operating systems are good enough if we do a little jerry-rigging that isn't too hard to live with, right? We'll find out. But yeah, a big part of it is either a new file format itself or at least new tools for making the existing file format so easy to work with that that you get new benefits out of it just from having known it. And maybe that'll include things like intermediate file formats that then render back out to the existing ones and stuff like that, right? So we'll find out. I'm not sure where it'll go, but it's a research project. So it starts with gathering information and then hopefully generating ideas will come from that down the line. All right, boom. Yes, reload it. Rerun. Rerun this one. All right, cool. So I have all the same sections now, although many of them are just totally empty. I've at least got that part to match up. So looking at what matches up line for line, the headers are the same up until this chunk that we don't know what to do about. Something funny there we don't know about. This matches this. Right here we have a time date stamp. I think it should be fine for that to just stay 0 in this. But we could... I mean, guess we could just take the hit and say, like, let's do it right. Let's do it right now. Just get everything right as much as possible, so that later if we want to figure out what the bare minimum is, we can do that by subtracting from our generator rather than constantly adding stuff in, right? And wondering if we're still missing something all the time. So timestamp. How are we going to get a 32-bit timestamp? What do I have for getting date time as time right now in my base layer? Time. These are Win32 helpers. I want the... Okay, I can get a date time in a spread out form like this. I can get a time in current number of ticks. I don't have any way to get a timestamp. Um, let's take a look. That might need to be something we do over here. OS now universal time, system time, Win32 system time to timestamp. Okay, we've done get system time. Hmm. Let's see here. What's happening with their timestamp? We generated this today, and the timestamp they wrote in does in fact look like. Okay, and okay, so we want a time 32 from a system time is what we want. Unix time to file time is basically doing time t int 32 times 1, 2, 3, 4, 5, 6. So we're talking about 1,000, a million, 10 million. Plus this amount of bias gives us the 64-bit file time. Okay. What's the deal? Why can't I go back? Okay, so we're gonna need, we have universal time here as a date time, local time from universal time from local time. I'm gonna need something like OS timestamp 32 from date time, I think. OS universal time from local time. So here we have system time, time from date time. Yep, so that does the conversion into a system time. System time to file time. And then we need to do file time is a 64-bit integer by going that plus high date time 32. And finally, U32 result is going to be the file time in 64 bits minus this divided by this. Okay, I have no idea if that's accurate. I just grabbed that off of Stack Exchange. Let's do a double check here against the first one we read. This is a different way of writing the same thing, but maybe I'll take this one. So first we want to divide by the rate. So this gives us the number of milliseconds since the Windows epoch, and then we do this to shift the epoch to the Unix epoch. Get the universal time. local time from universal time. Timestamp equals OS timestamp 32 from date. Okay, when I do that, yes, I reload it. Now I get, well, that's off. February 27th, 1977. So we did not nail it. We did not nail it. Although weirdly, my number is bigger. This one is small, or this one is big. It says February 27th, 1977. This one is small, and it says August 13th, 2024. Wait, no, this isn't small. This one is small. It's little endian, right. So this is the most significant digit. Got it. Okay, so what we need to do now is get one of these that actually works. So this didn't actually work. I'm just double checking. The high is going up there. The low is going there. File time 64. Dividing by 10,000. Sure that this is in 64 bits as well. Yep. There we go. August 24th. Oh, that's still wrong. It's August 24th at 2007. That's closer to the right thing, but it's off by about 2 decades still. So, not there yet. Okay, so that made some difference. I Okay, so I'm dividing by too much. It should be divided by 10,000, not by 10 million. Yes. And that gives August 25th, 2070. Okay, so it's still pretty wrong feeling. I think the problem is they're going for milliseconds instead of seconds. Let's try this. No, that didn't do it. Time 32t or time t. Don't love that. Let's try using this one that we saw earlier in converting. So they are multiplying by 100,000. So I'm dividing by, or 10 million. I'm dividing by 10 million. They're adding in this much. What if I subtract out that much? Yes. It's a little bit too big. Okay. That's not it. That's not it. are we missing here? This is what you do if you've already got a timestamp. Seconds since the midnight of January 1st, 1970. Maintained primarily in the form of 64-bit file time texture, which represents the number of 100 nanosecond intervals since January 1st, 1601. Okay, and so the order must be wrong. Right, because if the way you convert this way does first multiply, then add, then going the other way must be first subtract, then divide. And that gives us July 28th, 2026. Okay, so not correct either. But very close to the right idea. What could be off? Make sure I got the right number of digits there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and 10 million. 2, 3. Just making sure this is correct. LL. Man, that's all over the place. How did it just change so dramatically? Something is a little more off than I think I realized. Flexen asks, what are you trying to do? I am trying to get a 32-bit Unix style timestamp from the Windows operating system. Yeah, that might not be a bad idea. An LL there to make sure it's doing that in 64 bits. June 7th, 2075. Yeah, it's still just jumping all over the place. Like it's got some kind of entropy problem. October 19th, 2024. We're in the right year that time. The fact that it changes so much just over a couple seconds means there's something else going on, right? Like if it was changing by the right number of seconds every time, then it would be an offset. If it was changing by like, you know, a year every minute, then it would be the divider. But there's something else. It's just like rolling and rolling. It could be a truncation problem. It could be all kinds of things. So we need to go I need to just go look. I need to step through it. I don't have it. There's nothing else I can do here. I need to see what's happening. So first of all, what does it say the local time is? Let me just make sure that part is coming out right. It's saying that we are in year 2024, month 8, day 13, hour 10, minute 49 minutes and 55 seconds. Okay, so the local date time is correct. That matches what I have here. Then I ask for it to go back to a system time. 2024, month, day 13, hour 10, minute 49 second. Very good. System time to file time. So our file time has a low part and a high part. When we combine those, we get a file time 64 that looks like this. Now, that number there represents the number 1, 2, 3, 4, 5, 6. The number of 100 nanosecond intervals. So here I'm dividing out 10. Or I want to turn it into, so how many 100 nanoseconds are there, intervals are there in a second? Well, 10 of them gives you a microsecond. 10 million of them gives you a second, right? So this is how many seconds there have been. But then this thing here is supposed to be yeah, that's a very small amount of difference. If I take that number, file time 64, and subtract out this, let's compare them. Yeah, that's a very, very small difference that makes. Paul Paulson, you also worked on generating your own P file. That's awesome. Yeah, it's a lot to learn about it. So this is when they are converting from T, they add that in. So it seems like it should go the other way. It seems like I should subtract that number if this is correct, but you know, who knows? Is this correct? I don't know. Also, I don't know if I've got like the whole number that they're trying to give me. Yeah, it's just not big enough to make a huge dent. That's subtracting out. Well, let me see something. How many seconds is this? This is supposed to be 1, 2, 3, 4, 5, 6. Okay. One, 1, 6, 4, 4, 4, 7, 3, 6, 0, 0. So let's say I've got roughly 365 days in a year. $24 hours in a day, 60 minutes in an hour, and 60 minutes in a second. We got 369. 1601 plus 369 gives 1970. So that is what we would want to see. That makes sense. Right, this divided by that gives us the correct number of seconds to get from (1601) to 1970. Right. And so if I do all of these steps, if I do this much here minus give me this part, this much here minus this much here, I get this. It's a small change. And if I get all of that divided by 10, 1, 2, 3, 4, 5, 6, I get this. If I take that and I cast it to a U32, then it wraps. It just doesn't. It's just too big. I don't get how that's gonna fit. Something's not right. You know what I'm saying? Like, This right here must be wrong. So there, I just got a very different looking file time that time around. Now my file time is looking the same every time. But I'm still, oh, none of these actually use file time 64. So let's say file time 64 minus this amount. File time 64 minus this amount divided by 10 million. All of that. Truncate it. There we go. Okay, so I'm curious. Does the bit shift operator have a lower precedence? Is that what I messed up? If I do this again, U64 here, plus this. Okay, so we have the low part, and then the high part being added together. But now I've parenthesized it for sure the way it should go. Yes. And we get August 13th, 10:58 a.m., 2024. And if I drop these parentheses, I get complete chaos. Okay. Yeah, okay, so I guess that was my bad. I thought the bit shift operator would be higher precedence than the plus, and therefore that this would get bit shifted and then added. But I guess what was happening is these were getting added and then bit shifted, which was useless. Okay, that's fine. So now we can get the timestamps correct. Moving on, pe.h, COFF header, symbol table. Well, Volbus, I'm pretty sure that I was right then. Like, it having the lower priority is the problem. Look, let me show you again. Right here, right? I build this and I run it. Okay. Yes. We get the right time. Okay. All it takes to break it is to unparenthesize these, which means plus has a higher precedence than bit shift. Right? By taking away the parentheses, the only thing that could possibly be different is that now the plus is higher precedence than the bit shift. Boom, and now it's not working. Right now it's giving me garbage. So it is the case that bit shifting has lower precedence, and because of that, the parentheses fix my bug. I would have thought that the bit shift has higher precedence, and that's why I assumed I didn't need the parentheses for a little while there. So I do think I identified the bug correctly. Does that make sense? Yeah, this is definitely working. Yeah, I should have just put parentheses. For some reason, I thought that bit shift was going to be like a multiply. That it would bind higher. I was thinking of bit shift as multiply. My mistake. I shouldn't do that. Bitwise operators always parenthesize. Always, always, always. Definitely the right thing to do. Okay. Now what we need is, right, I'm going comparing bit by bit here. Here is the, oh, let me make sure I'm not, okay. Okay. So we got the timestamp correct. Next up we have pointer to symbol table is a 0 on both of these. The number of symbols is a 0 on both of these. The size of the optional header is F on both of these. We have an executable image. Ooh, this has executable image and large address aware. Okay. Zero on that, 0 on that. PE32 plus, PE32 plus, major link. We're gonna not put in a linker version because we are the linker. We're a different linker. We're linker version 0. Size of code. Okay, here it's got a big old size of code, and I didn't see any sign that size of code needed to be a multiple of the alignments or anything. And this also is kind of confirming that. It looks like this would be like a multiple of 512, but not a multiple of 4096. So it should be fine. Size of initialized data, 0, 0. For me, okay, address of entry point, 4712. My address of entry point is 4096. That should be fine, considering we're both putting the text section at 4096. They just have the address, the entry point shifted in a little bit. Interesting. Let me check that. Let me check that out. They're saying right here in chat that if I don't generate the program with a linker, that the accepted practice is to put full bytes, fill the bits, version minor. Entry point v off, image base, address of entry point, base of code. Base of code. So I don't have a base of code. I probably want that. Image text v off. Yeah. Okay, so total text size, entry point v off, opt header dot text v off is going to be kilobytes 4. That makes sense because 00 could actually be a version number, whereas 255 is like the end of the range. If you're going to reserve something for 00, you wouldn't necessarily reserve. That makes sense. Yes. Although I might end up considering my thing a linker in time. Size of code, size of initialized data, address of entry point, base of code now matches. Image base. Okay. My image base. Okay, so our image bases are the same. That's cool. Virtual section alignment is the same. Raw section alignment is the same. 512. Major operating system version. Let's just copy that. Major operating system version. You started with an assembler program instead of a C program. Right. That probably would help because I'm comparing this against, even though I made it real small in the C code, it still came out as several kilobytes, you know, like 40 or 50 kilobytes of executable file. Just from linking and everything from C. Okay. Major version, minor version, major image version, major image version, minor image version, major subsystem version, major subsystem version, subsystem version, major, minor, Win32 version value 0, 0, size of image is much bigger here. They're going for a little over, what is that, 10, 6, little over 6 kilobytes, or a little over, not 6 kilobytes, geez, much more than that, little over 64 kilobytes. Size of headers, checksum, subsystem CUI, dynamic base high entropy, terminal version NX compatible, size of stack reserve, so those four all look good. Post loading, that's all the same. Number of RVAs and sizes, 16, 16. Okay. So I've made a certain amount of progress getting them to match. Let's see if we've got a minimal runnable program yet. This app can't run on your PC. Okay, still doesn't run. Let's take a look at the data directories now. Actually, I'm going to do that, but I'm going to take a 5-minute break. I've already been at it for 2 hours. I've been at it for 2 hours and a half already, and honestly, it's probably enough for one day. I mean, we have a lot farther to go, but being on stream all day, it's a little rough on me. So I think we'll pause here. We know that the next step is to pick up with the data directories. And I'll probably do this again tomorrow around the same time. Or, no, probably I'll do it Thursday. Probably I'll do this Thursday around the same time. So yeah, if you want to see more of this, I think we'll pick it up there and we're going to keep working on trying to get generated.exe to actually run. And we'll see if we can get there. I might need to create another example program. Oh, 90, it's not even 50, it's 90 kilobytes, just to link in all the C stuff. Man, it's crazy. But yeah, we'll pick this up, and for now I will wrap things up. So if you liked these projects I'm working on and you'd like to see me be able to continue working on them, don't forget that I am counting on viewers and anyone who's interested in my projects to go and check out my membership program on mrforth.com/membership. And if you support, you're helping out, and you also get lots of cool stuff, including you can spend all that money that you spent supporting me to also buy the stuff that I ship. So when my PE investigator generator libraries and utilities come out someday, all the money you spent supporting me, you won't spend it again to buy that stuff because of the credits. You get lots of cool stuff along the way too, so consider that. It's a big help when people choose to support the lab, and I will be around the internet. So see ya. Bye bye.